Great. Well, welcome everyone. Thank you so much for joining our Recovery Ventilators course with Nick Brown today. He's from Build Smart Group, and we'll be getting started in just a couple more minutes. I just have a few slides to go over first. Next slide, please, Nick.
Thanks, and we've got some chatter in the chat already. Filters, whether the new code will require them, and just the comment that their engineers and consultants are already recommending these based on unit sizes and green building. Okay.
You
Love
could
to
just,
talk more about that.
yeah, if you go to the next slide, please, Nick, that'd be great.
You got it.
All right, so before I turn things over to Nick, I'm just going to go over a few Zoom reminders. I'm Naomi. I work with 3C Ren out of the county of Santa Barbara. Just a few quick Zoom protocols. Please make sure you're on mute for the duration of the training. We encourage questions. Please use the chat or raise your hand, and we will invite you to unmute. The session is being recorded, and the slides and recording will be shared with you within the next few days. Just a reminder that this training is eligible for both AIA and ICC learning units. We're going to be distributing the learning units based on Zoom attendance. So if you would like to receive learning units for today, please make sure you're joining at the link sent to you after registering. And if you have any questions about learning units, I'll put my email in the chat later in the course, and you can reach out to me there. Next slide, please, Nick. Just a quick reminder about 3C Ren, or maybe it's in your first time joining one of our courses. The Tri-County Regional Network, Energy Network, or 3C Ren, is funded by ratepayer dollars that we pay through our utility bills through the public goods charge. And the benefit of being funded by ratepayer dollars is that there's no cost to those that we serve. And as a regional energy network, we're able to return these dollars back to the local economy, which has historically missed out on some of these funds. Next slide, please. We currently offer 6 programs focused around 3 services: incentives, training, and technical support. This training is part of the Energy Code Connect program. You can see additional trainings being offered and learn more about our other services by visiting our website, 3cren.org. But as you can see, we have a home energy savings program, which offers incentives for single-family homes and multifamily homes. We also have our building performance training program, which is another thing that we offer that provides training to building professionals. And we also have technical assistance for both agricultural energy solutions and energy assurance services. Next slide, please. Since 2019, 3C Ren has had over 4,000 individuals attend trainings. We've answered over 334 Title 24 and Cal Green questions, and we've secured $155 million for investment in the Tri-County region. And we've also completed 1,374 energy saving projects throughout the Tri-County. And we're excited to continue growing in these areas in 2025. And with that, I'll pass things over to Nick to get started with today's training.
Thanks so much. Got a good sized group this morning. Our topic today, recovery ventilators. That's the term I'm using because HRV/ERV is really unwieldy. And it gets you right to that fundamental question, and everyone sort of gets paralyzed. Well, do I need an HRV or an ERV? What's the difference? So anyway, I call them recovery ventilators. And so we'll talk about this from the standpoint of healthy buildings, energy code compliance, both the requirements and the optional performance credits. But I'm a big proponent. I've got one in my main house and one in the ADU I built. Did it mostly for indoor air quality reasons. Here's my house in Long Beach. I'm a little south of most of you. I'm in climate zone 6. And I run a consulting firm called Build Smart Group. We do Title 24 compliance work, but full half of my time now is teaching classes on the energy code, but also how-to classes on electrification, on recovery ventilators, heat pumps, heat pump water heaters. There's a lot to teach in this transition to cleaner energy. So my main house was a deep energy retrofit in 2014, since converted to all electric. There's a blog post on that journey titled What We Learned When We Went All Electric, if you want to check that out. And then you can see the ADU we built above the garage in 2022. That was built all electric from the start. And we have a nice couple living there going on 3 years now. They've got a heat recovery or an energy recovery ventilator in the garage where I can keep an eye on it and change the filters. And they have no idea the benefit that that's providing to their health. But I feel good knowing we installed it. I've got the time organized today like this: what they are, how the energy code requires mechanical ventilation and where, how recovery ventilators work, energy savings, compliance credit, and tips for actually specifying and installing them. Looks like, based on the comments in the chat so far about your specific learning objectives, this should be pretty on target. But please stop me, unmute yourself, blurt it out if that's allowed. If there's anything you'd like to stop and discuss, I'd rather do that than saving things to the end. I vastly prefer interactive classes to those where people are passively sitting back, like receiving the information and not participating. So please take me up on that. This class makes use of a lot of research that was funded by actually SoCal Gas and Small Planet Supply, which is a recovery ventilator distributor, where we looked at the energy impact of having heat recovery in homes. That was back a few years ago that I did along with Luke Morton, if you know him. So we started using this Slido app to build engagement on our virtual classes. And then they sent me an invoice from Slovenia to renew my subscription, which I had no way to pay. So I've left in these conversation starters, but you need not switch to the Slido app. We're just going to use them as conversation starters. Put your answers in the chat. So what does heat recovery ventilators make you think? Help me out here. I don't want to cold call people like a bad law school professor. Gabriel, good answer. Outside air, moisture neutralization, yeah. So those are both engineering perspectives. Yeah, system to bring fresh air in. More efficient and comfort-oriented solution to code-required ventilation. That's a very nice answer, Zach. Yeah. And George wants to cover the how-tos of it. Where to get inlet and outlet air from. Miracle appliance. Okay. Oh, very good. All right. Here's the slogan I came up with. They let you live better, sleep better, and work better, and make your HVAC run better. But I like your answers too. So reasons to consider installing these. Indoor air quality, number one. Recovery ventilators provide continuous ventilation for indoor spaces to dilute pollutants and enhance indoor air quality. So far, the best technique for reducing pollutants in indoor air that we've come up with is mechanical ventilation. Of course, also reducing pollutants in our indoor spaces is the other approach, but we can't entirely eliminate indoor pollutants. It comes in on our furniture and our rugs and the soles of our shoes. So hence the need for mechanical ventilation. They ventilate much more effectively than spot ventilation, such as a bathroom exhaust fan, which is the most common technique for accomplishing continuous mechanical ventilation in the state. They also keep balanced or neutral pressure instead of negative or positive pressure, which improves control at the moisture barrier, the air barrier, generally a little bit more comfortable to be in too. Then there's the energy savings arguments. As was said in chat, I like to use this term, they temper the incoming fresh air using the outgoing stale air. And this reduces the burden on the space conditioning system in winter and summer. There's also energy code compliance reasons to embrace this technology. They're one of the most powerful compliance credits available in the software using the performance method, because they save on the energy needed to condition that outside air coming in. So by using these in your energy compliance models, you can compensate for features that use more energy than standard, like big sliding glass doors and skylights. And then health. They allow you to boost ventilation in your home when needed. Some of them do it on an automatic basis. Others have a control panel. So this might be necessary when you have a big party and lots more people in your space than normal, or when there's another health scare like COVID where you want to have a higher ventilation rate. And also the distribution of fresh air in your house is imperfect when you have one fan or two fans providing that functionality. Instead, a ducted system that moves the filtered fresh air behind closed bedroom doors at night into home offices, while simultaneously taking out stale air from the most likely areas to need it, the bathrooms, the kitchen, allows you to have better health outcomes and perform better at work. So let's ask next question. How experienced are you with these, folks? Are you installing them occasionally on your projects? Do you put them in every project? Or are you new to these? Okay, a couple folks new. Yeah. All right, good to know where you're coming from. All right, let's start next with the code. Okay, Zach's specking them, and Martin's looking to do more of it. Thank you. So let's start with what the code requires for mechanical ventilation, because these are a tailor-made in a box system for meeting these continuous mechanical ventilation requirements. So the two things we can do to improve indoor air quality from a building science perspective: source control. So that means instead of having plush carpets that can accumulate pollutants, we have hardwood floors, linoleum floors, tile floors. It means storing chemicals out in the garage instead of under your kitchen sink. It means choosing furniture and foam mattress toppers with intent to not bring so many of those pollutants into our home. But this is not a sufficient approach to completely ensure indoor air quality. The dilution of those pollutants is necessary to really ensure continuous indoor air quality. And so that's done with mechanical ventilation. There's two classes of mechanical ventilation in the code: spot sources, or on-demand mechanical ventilation. That includes your bathroom exhaust fan that you turn on whenever there's a source of moisture in that spot. And kitchens, your kitchen range vent hood, which is there to remove the pollutants you create during the cooking process, the moisture you create during cooking. So those are the occasional use spot mechanical ventilation. Those are separate from what the California Energy Code calls the IAQ fan, or whole home fan. That needs to be operating continuously or some intermittent operation schedule that's equivalent to that continuous operation. So mechanical ventilation is specified in a couple of ASHRAE standards. These are nationwide, really international standards. 62.1 for non-residential buildings and 62.2 for residential buildings. And then Title 24 rubber stamps these ASHRAE standards, usually with a few exceptions. So here's a couple of quotes on why we need to worry about indoor air quality at all. The CEC, in increasing required ventilation rates following ASHRAE updates, said increasing ventilation rates will reduce respiratory illness and associated sick leave, reduce sick building symptoms, and increase productivity. And then this Harvard study found that reduced ventilation brought down people's ability to think and perform higher order analysis by 60%. These charts show it. There's three different metrics being shown here: information usage, breadth of approach, and strategy, those higher order level functions. And as CO2 concentration in parts per million goes up from 500 to 1500, you can see that these scores are dropping precipitously, especially information usage and strategy. So if you have a challenging job like I do, it can really pay to make sure that your parts per million CO2 aren't approaching these levels. So it's a seldom thought of function of our buildings that they're helping our cognitive function. They're helping our health. But that's what I hope you come away with today from a building science standpoint. Why are we even requiring mechanical ventilation? Now, here's the first mandatory part of the energy code. I've cited the code passage here. This applies to new single-family homes. So kitchen range vent hoods need to meet a certain minimum CFM or capture efficiency according to the size of the dwelling unit. And this is really going to drive home this pollutant way of thinking for you. What do you see in terms of the airflow requirements as dwelling units get smaller? From 1,500 square feet to 750. And this was counterintuitive to me when I first saw it. A large home needs 110 CFM over an electric range. A small home needs more, 160 CFM. Why would that be? Because those pollutants you're creating are the same. you're cooking a given meal in a smaller home, those pollutants are higher concentration. There you go, Zach. So you need a higher rate of removal in a small apartment than you do in a large mansion. So this flies in the face of equity and affordability, of course, but it's what the building science says. The other thing I want to show you about this table is that when you install a natural gas range, the CFM requirements are higher than when you install an electric or induction range. This was the first code cycle that made this distinction, and that's because cooking with gas creates additional pollutants that need to be removed quicker. We've had some chatter on the Quebec discussion forum recently about these 250 CFM minimum airflows, and can that even be achieved by many microwave oven hoods these days? Difficult to find, and certainly not every manufacturer meets those. But in all cases, these vent hoods also need to be able to operate no louder than 3 zones. And these are HERS verified measures. Now, not direct measurement, but they'll look at the nameplate of the range hood you've specified and make sure that it meets the requirements. So in terms of a best practice, I'd encourage you to insert this table into every plan set you create with a red box around the dwelling unit and the type of range you're installing, just so it's clear what needs to be installed. That's one of those measures that could easily be missed. All right, so most new homes, which are required to have continuously operating mechanical ventilation, do it something like this, with an exhaust fan in a bathroom running continuously. The energy code recognizes these roughly as equal approaches: exhaust ventilation, supply ventilation, where you're blowing in from outside a certain CFM, and balance ventilation, a combination of exhaust and supply ventilation running at the same time. That keeps neutral pressure in the space, but it uses more energy because you've got 2 fans operating concurrently. So here's an illustration we created to talk about the pressure difference. With exhaust ventilation like shown here, the exhaust fan is mounted somewhere in a ceiling, exhausting to the outside, taking stale air from the home. That creates negative pressure in the space. And that sucks in outside air through tiny holes in the building envelope. I don't care how well you've built this house, you've got tiny holes. So that's the source of your fresh air. That could be from your side yard where your pets use the bathroom. It could be coming from your garage or the raised floor, the crawl space under your house. So it's uncontrolled, right? You have no way of regulating where that air is coming from. It's also not filtered unless you assume that your building envelope is doing a magical job of filtering it. I've read that in some articles. I don't quite buy that. On the other hand, balanced ventilation, such as recovery ventilators, can do. Here's the first diagram I'll show you. They're pulling in fresh air from outside. That could be up, down through the roof or in through a wall, lots of different ways to accomplish that. Then it's running that fresh air from outside through a filter in the recovery ventilator box. And it's bringing that tempered fresh air into the house. That's the orange arrow. At the same time, it's pulling stale air from the home. And although the airstreams never cross, they swap heat. Okay, that's a heat recovery ventilator in that heat exchanger core. And then that stale air gets taken outside. So as a result of having roughly equal supply and exhaust airstreams, you have neutral pressure in the space, and you don't have the same air infiltration from uncontrolled sources. So in this manner, we're bringing in a more controlled set of outside air. And the energy code has a mandatory measure that says all supply ventilation systems and supply legs of balance ventilation systems must be filtered MERV 13. Okay, just like your return filter grill in a ducted HVAC system has to be filtered MERV 13, we want to get the outside air coming in the same way. So that means that you're going to need to either install a MERV 13 filter in an aftermarket way if your recovery ventilator isn't equipped with that, or hopefully you find a manufacturer that has that as an optional module. Because recognize that outside of the state of California, no one's requiring MERV 13 on these systems. I found a manufacturer that'll make them to fit the HRV in my house, and I just order these MERV 13 filters as needed to fit my recovery ventilator, because it did not come with that standard. How much ventilation is required? Oh, how far apart are the air streams? Yeah, there's some guidance on that. I think I've seen minimum 6 feet. You certainly don't want them commingling, do you? So the farther apart, the better. They also make pant leg distribution fittings that the supply and exhaust both hook into. That's why they call it a pant leg. And then those two airstreams are brought out through one penetration in the building envelope, and they've got some means of ensuring they don't overly mix. Of course, it's not going to be as effective as actually splitting up those airstreams, but I did use one of those pant leg penetrations for the ADU, just for simplicity. So the ASHRAE standard and Title 24, which adopts those ASHRAE standard, calculates the minimum required ventilation rate using this formula. The total ventilation rate is a function of the conditioned floor area and the number of bedrooms. But then why are we showing different minimum CFM for different climate zones, you might wonder? There's no climate zones in that equation. You'd be correct. The reason is our climate zones all have different assumptions on wind speed, and wind speed affects infiltration through the envelope, and infiltration through the envelope is outside air. So the more infiltration you have, the less airflow the fan needs to do. So basically these climate zones with lower CFM required for the fan have higher wind speed on average in the assumptions. But look at the numbers. We're looking at 85 to almost 100 CFM for a 2,700 square foot home. A few code cycles, this would have been 20 or 30 CFM lower. So over time, they've decided higher airflow is needed. And a 50 CFM bathroom exhaust fan is not going to do it, is it? You're going to need 2 bathroom exhaust fans running continuously for this size home. Another reason that recovery ventilators are a great way to go rather than just relying on exhaust ventilation. Yeah, for high occupancy spaces, and I assume, Hank, you're talking about non-residential buildings more than single-family homes, because single-family homes are using this formula, number of bedrooms and conditioned floor area. That should scale pretty well. But non-residential buildings have ASHRAE 62.1, which have more of a formula using the expected number of occupants, like 15 CFM per person. Good question. And the indoor air quality fan will show up on your energy code compliance report automatically if it's required in this box. Here you see an 84 CFM exhaust ventilation fan being used to meet the mechanical ventilation requirement. This is always going to appear just before the final page with the signature. What about COVID? Well, after COVID, many building owners, especially institutional building owners, set their airflow rates higher than code minimum. This is in recognition that higher ventilation rates do a better job of ensuring pollutants and germs are removed from the building. Filtering return air also became more important. So some buildings, if they were able to, upgraded from MERV 6 or MERV 8 return filters to 11 or 13. And some even installed air cleaners and UV lights to disinfect the air. This study that I'm showing here found that setting ventilation just to the code requirement was equivalent to vaccinating half to 60% of the occupants against the flu. I thought that was a pretty strong argument. And yet many of our older buildings still don't have continuously operating mechanical ventilation systems. That was never required when they were built, but a good idea to retrofit them. Now, I sat in on this Stephanie Taylor, who's a medical doctor. She's founded this 40 to 60rh.com nonprofit. And she had this great quote. She said, "You building designers have a bigger impact on health than we clinicians." Think about that for a second. In one of the hospitals she was working in, they had wood paneling. Darn architects put wood on the walls of our hospital, and it was peeling off the walls because it was so dry in there. We added humidity to keep the wood trims on the wall, and we're shocked to find infection rates went down as a result by accident. This is why she advocates for this range 40 to 60% relative humidity as the sweet spot, where certain things that happen when the air is really dry don't happen, and certain things that happen when the air is really moist don't happen. So good rule of thumb. And of course, ventilation plays a big role in that. Now, many of you may have come for this question. What's the difference between ERVs and HRVs, and which one's right for me? First, the difference. ERVs, energy recovery ventilators, enthalpy recovery ventilators, if you want to be a little more building scientist about it, they have membranes that in that heat exchanger core allow moisture to flow through them in the air, water vapor. Okay. Whereas heat recovery ventilators do not. They just swap heat. Okay. So ERVs swap heat and moisture. HRVs just heat. So that means that some of the humidity in the outgoing air goes into the incoming fresh air, but only in an ERV. And I would ask you to consider, is that always a good thing? Is it sometimes a good thing? Is it never a good thing? These are nuanced questions, which is why this ERV, HRV debate is so common on message boards. It's something with pros and cons and no simple answer. Title 24 doesn't care. They want the heat recovery function. They don't care. They don't regulate about the moisture exchange. But occupants might care. If you're in a mild climate zone, generally, people say, well, an HRV is probably okay, maybe even better. If you're in other climate zones, ERVs are certainly better. So I turned to my favorite building scientist, Allison Bales of Energy Vanguard. If you don't already read his blog, it's fantastic. It's well written, accessible, but he covers interesting building science questions. And he says the choice between an ERV and an HRV should land on an ERV most of the time. It's only in mild climates where it doesn't get too cold, humid, or dry where HRVs make sense. And in my experience, ERVs don't cost a whole lot more. So yeah, you might as well just go with the ERV. I'm reading Zach, your comment here. Yeah. Yeah, humidification is not something we measure on our thermostat generally, is it? I have some air quality monitors that I wanted to show you that do measure relative humidity as well as temperature and CO2. This one's called Aware. I've also got one over there that also measures NOx emissions. So that's kind of cool if you're in a gas combustion house. That's called, I'll get that name for you later. The point is, if you want to worry about your relative humidity, you can using these meters. And conceivably, you could turn on a humidifier when your indoor relative humidity falls below 40%. And if you got a dehumidifier, do the reverse when it got too moist. Let's turn next to how these work. And if there are any questions so far, please put them in the chat. I like this cutaway diagram from Fine Home Building that allowed me to use it. So you see the fresh air intake, that's the blue duct. It looks like here it's coming from an exterior wall, perhaps in a basement. And that's bringing in the fan in the unit is bringing in that fresh outside air, hopefully running it through a MERV 13 filter in the box. And then that air continues in the blue ducts as supply throughout the house. You're showing one in the bedroom, one in the living room in this simplified cutaway. At the same time, a different fan in the box is pulling stale air out of the house. Generally, the kitchen and the bathrooms are those spots that are chosen because they're spots with additional moisture that needs to be removed, right? Also smells, but mostly for the moisture. And then that pink ductwork goes into our box. The two streams swap heat to some extent, not 100%. This is the term called recovery effectiveness that measures what portion of the delta in temperature between the two air streams is captured. Okay, and if it's an ERV, they're also swapping some of that moisture, right? And then that stale air continues out of the building, right? So I generally recommend each bedroom and living space gets a supply grill. Each bathroom and kitchen gets an exhaust grill. And they don't have to be the same number of ducts, but recognize the total CFM needs to be roughly the same. So if you've got 8 supplies and only 3 exhausts, then those exhausts are going to need to be higher CFM So that's the danger of having a big imbalance between number of spot registers. In general, it's good to have those fairly close to one another for that reason. Here's another cutaway of the heat exchanger core. You see this one is showing kind of standard filters of the exhaust and supply. All those are doing is protecting the fans from wear and tear, catching the bugs. In a code compliant California installation, you'd have a MERV 13 filter on that fresh air from outside. All right. And I think I've got, yeah, here's a little dramatization of the temperatures involved. So in winter on the left, let's say it's 40 degrees outside. If you were running an exhaust ventilation strategy, you'd be getting 40-degree air in your house that your heater would have to compensate for. Instead, we're using the 70-degree stale air from the home. We're using the heat exchanger to swap most of that heat, and the 40-degree air becomes 60-degree air before it hits your house. So that's a much lessen burden on your heater to condition that outside air, okay? In summer, maybe your worst day is 100 degrees outside. You've got 75 degrees stale air in the house. Maybe that air enters your house at 86 instead of 100, lessening the burden on your air conditioning. Make sense? I kind of find that putting some numbers in an example really illustrates it better. Keep in mind what's happening here too. The fans generate heat. They move air, but they also generate heat. And that heat's, some of it, going into your space. For that reason, in winter, recovery ventilators generally perform more efficiently than in summer because you're getting that fan heat energy helping heat your outside air, whereas it's taking you in the wrong direction in summer. Just something to think about. That's one of the reasons why recovery ventilators aren't a good choice in Palm Springs, right? A cooling dominated climate zone. In a summer night, it's cold outside, warm inside. So it's cooled out in the evening. Does an HRV prevent the indoor heat from venting out? I think what you're asking is the HRV smart enough not to swap heat when it's unfavorable? Some are, some aren't. Most aren't. Most, it's a bargain you make that you run it 24/7. Most of the time it's beneficial. Some of the time it's slightly less beneficial. But some of them have summer cooling bypass function, for instance, that does exactly what you're talking about. When it's cooler outside, it routes the air around the heat exchanger core. So you're bringing in fresh filtered air without heating it up. Good question. We were going to talk about that, but it came up earlier. All right, just so you know, I know something about these. Here are mine. The one on the left was done as a retrofit in my main house, so it's up in the attic. The attic is not a perfect spot for a recovery ventilator. You have to get up there to change filters. It's in a hotter, colder space than is optimal. But that's where I had to work with. When we built the ADU above my garage, I put the one on the right just under the floor where I could change the filters and monitor it. And that's a much better spot for it. Now, I like to share real world data on these to get you thinking about how they work in practice. The ADU one has nothing special fans. They're not ECM fans that are extremely low energy use. They're just standard fans. And so it moves 60 watts, uses 60 watts to move 60 CFM. So 1 watt per CFM. That's not a very efficient recovery ventilator. They make them down in the 0.7 watt per CFM range, even better than that. And then you can see the little boosts where the energy use is bumping up. This is my energy monitoring system shown here, a period of about a week. And you can see when it senses moisture in the bathroom, this particular model goes into boost mode, which is a really nice feature. Here are the temperatures to show you the heat tempering of the outdoor air. This is June to December in the ADU. It's a 1-bedroom. And the outdoor fresh air temperature is shown in blue. So you can see it's going almost to 100 at the end of August. It's going down below 50 in November. That's the Long Beach climate. And the supply air to the inside is shown in red. Notice how much less extreme that is, right? So there's the tempering shown in graphic form. But also notice the supply air isn't right in the middle of the outdoor air range. It's bumped up a little, and that's the impact of the fan heat. Okay? Makes sense? So the summer, temperature up to the hundreds, and it's getting in the high 80s. In the winter, temperatures down in the high 40s, and supply air in the mid 60s. Makes sense? What about the CO2 picture? That's what it's called, Yoo-hoo, my other air quality monitor. So I monitored this in our master bedroom before we had the HRV installed. And we saw spikes of 1,000 to 1,200 CFM. Because keep in mind, your HVAC system isn't running all the time. And even if it is, it's recirculating air inside the house. So CO2 tends to accumulate behind a closed door in a room, especially when you've got, 2 people sleeping in there. Once I put in an HRV port, I think it's 20 CFM or something, not a whole lot. The spikes were limited as shown here, more like 700, 800 parts per million. And the hope is we're getting a more successful sleep as a result of improving the indoor air quality. Let me just admit, Halit. And so here is my where I took it to an Airbnb over Thanksgiving. That's the picture on the left. And those bars tell you temperature, humidity, and that middle one, CO2. So see how when we woke up in the morning, the red light was on and CO2 had spiked. This is a house that probably has no mechanical ventilation system installed because it wasn't required when the house was built. This was in Palm Springs somewhere. On the right is a rare moment in time where I scored 100. Everything was everything was down low, so I had to take a picture of it. So highly encourage that. How much CO2 is too much? The Earth, I had to update this. When I taught this last year, it was at 421. It's now at 424. There are consequences of rising global CO2 levels, but we won't go into that here. So the Earth's level of CO2 is measured at one of the Hawaiian volcanoes because the concept is that there's so much air movement, there's good mixing, you're far from spot pollutants, good place to measure it. So we're at 424 just as a base level, all the air we breathe, right? And the Harvard study used 950 parts per million as typical indoor levels, 1400 as extreme. CBRE, a big property owner, when I sat in on one of their webinars, used 80 parts per million as their target maximum rate. Title 24 doesn't specify a maximum, but it does say when you're required to install demand control ventilation, this is only applicable in non-residential buildings, it uses outdoor concentration plus 600 as when that should add additional ventilation. So there's a few data points for you to consider: 800, 950, 1,000. So that tends to be the range that you want to stay in if you, at least from my research, not a whole lot of research out there will tell you, but certainly that 1,000 CFM range is what I've been trying to do. Here's another case study from my house. During COVID, my daughter invited 2 friends over to do high school in this very office. And I had my air quality monitors in there, and this is what it saw. At 7 a.m., under 1,000. By 9 a.m., it was going up above 1,000. By lunchtime, it was above 1,400. And so I was worried, hey, they're going to get sleepy. They're not going to perform that well. COVID stuff enough. Let's see what an HRV does. And that's what prompted me to install the main house HRV. I put 30 CFM into that classroom, and that kept the CO2 level under 1,000 parts per million, which was a victory. That was the precise goal. And I have that now benefiting my home office. Okay, questions so far before we look at how much energy can they save? We're going to 11 today, by the way, folks. Okay, I'm going to keep going. We did a study where we looked on an hourly basis across all 16 climate zones in California, the outdoor temperatures, the indoor temperatures, how much of that delta T gets recovered by the recovery ventilator. And we looked at typical recovery ventilators, which generally have higher watts per CFM and lower recovery effectiveness. And we looked at best-in-class recovery ventilators that have better numbers on both of those. We found savings of 11 to 15% in climate zones 1 through 5 compared to exhaust-only ventilation. Climate zones 1 through 5 are coastal Northern California from Eureka all the way down to, I think it goes to Santa Barbara, but not to Malibu, okay? We also found some savings in climate zones 10 through 14 and 16, 10 being Inland Empire, Southern California, 11 through 14 being inland Northern California, and 16 being the Sierras. But climate zones 6 through 9 and 15, we didn't see much energy savings. And that's coastal LA, coastal San Diego, Orange County, LA, and Palm Springs. Now, best-in-class recovery ventilators, going back to the second bullet, showed roughly double energy savings in those favorable climate zones. So let me show you the math of energy savings with these, because it's not an automatic that a recovery ventilator is going to save energy. Let's say this typical recovery ventilator uses 56 watts to move 80 CFM, whereas an exhaust fan would use half as much, 28 watts, running continuously. So annually, that extra ventilation energy is 245 kilowatt hours, okay? Let's say we're in climate zone 5, where many of you probably are, Central Coast. We have no cooling energy to speak of. We're not saving anything there. But during heating season, we're saving 290 kilowatt hours. So that means we just saved 45 kilowatt hours. But notice we used almost all the savings switching from exhaust to balanced ventilation because we have that second fan. And you can think of some climate zones where the heating and cooling savings might not outweigh the extra ventilation energy, right? That's the trade-off. Now, a best-in-class recovery ventilator, let's say, moves the same 80 CFM, but only uses 40 watts. Well, that cuts the extra ventilation energy down to 105 kilowatt hours. And by virtue of having a more efficient heat recovery core with a higher recovery effectiveness, now it's saving 395 kilowatt hours. So that's coming out quite a bit ahead, 290 kilowatt hours a year. See the difference? Now there's a whole study. I'm going to send you guys this slide deck with the links so you can, click on it and get more information as much as you want. But here is the impact of changing from exhaust to an HRV in a typical one-story single-family home with a heat pump with a typical recovery ventilator. Okay, notice in the far right, that's the extra ventilation energy that house is using compared to exhaust. That's the negative we start out with. But there's heating energy savings, cooling energy savings, depending on the climate zone. And so the HVAC savings is the sum of all those columns. That's the number we really care about. And you can see in climate zones 1 and 16, the greatest savings, right? Those are the most heating dominated climate zones in the state. Whereas 6 through 9, 10, 15, all show big negatives. You're actually using more energy than you would with exhaust only ventilation. Make sense? Now let me show you a best-in-class HRV in the same type home. The ventilation penalty is less, the heating and cooling savings is more, and so you've wiped out all the negatives except for 7 and 8 in the heat HVAC savings KWH column, and you've increased the magnitude of the savings. As a percentage, those savings in 1 through 5 are 16, 15%, right? Pretty solid. But they're a lot smaller in 7 and 8 and 9, the more moderate climate zones. Alan asked about best-in-class recovery ventilators, and we're trying to be brand non-specific, of course, with that term. But it's loosely based on the Zenders, okay, that are quite a bit more money, but have recovery effectiveness in the 90% range and watts per CFM in the 0.5, 0.6 range. That's all laid out in the study. But the top of the line recovery ventilators like this one, and again, we're not advocating any brands. I just like to cover real world in my classes. They can do other things like bypass mode to the earlier question on, can you just bring in the cold nighttime air when that's beneficial? We found 50 kilowatt hour savings were possible using that bypass mode in the milder climate zones that have that diurnal swing. Others have a boost mode when added airflow is needed, either as measured by a humidistat for moisture level or as measured through a CO2 sensor. So all kinds of cool things these units can do. So just to take pause and make sure, let this stuff soak in a little bit. what's the trade-off we make when we're using recovery ventilators in terms of energy savings? What are the pluses and the minuses in the ledger? Also, give me a chance to have a drink. And George, I have no idea who makes them here. With tariffs on the horizon, that might be important, huh? All right, the trade-off I was looking for was we're going to use more energy to move more air and add a second fan than exhaust. But the heat exchanger core is going to temper the incoming fresh air, which will save us energy on our HVAC. Plus upfront cost versus cost per kWh, right? Yeah, valid point, George and Mark. All right, let's look next at code compliance. I actually used the same wording that one of you guys did, miracle workers in a white box, because they really can have a huge impact on compliance. Here's the compliance impact measured in efficiency EDR, or energy design rating, efficiency and source EDR. Okay, this is a typical HRV.
Nothing, just.
And the average efficiency EDR impact's about 10 points, with climate zones 1, 2, 3, 5, and 16 the highest in the state. Source EDR generally follows the same. Best-in-class recovery ventilators boost that efficiency EDR impact about 40% on average. That's a huge compliance impact, 10%. The only other thing I can think of that has that size impact is a battery storage system or a variable capacity heat pump. That's about it. So this is a real nice feature to put in your homes that have a lot of glazing, or that for whatever reason can't reach prescriptive standard level of envelope, or really want to use a gas water heater. That's the benefit of these compliance benefits. It can outweigh whatever other sins are in your design. What about multifamily? We've been talking mostly about single family so far. Well, interesting. The code, first of all, is different for multifamily indoor air quality. Title 24, the 22 code, requires balanced ventilation in multifamily units unless the builder does blower door testing on all the units, in which case they can continue using exhaust-only ventilation. This was new for the 22 code. We didn't know what to expect. I thought most builders were going to choose balanced ventilation and avoid the blower door test and the uncertainty of it. What if you don't meet that threshold and you've already built your envelope? What can you do? But I was wrong. Most builders seem to be choosing to continue to use exhaust ventilation in their multifamily buildings and blower door test the units. Okay, but if you do use balanced ventilation, the standard design also has balanced ventilation. So there's no added fan energy penalty in the multifamily world. So the energy savings are larger and the compliance impact's larger, as you can see in this chart. Although you see the same climate zones performing worse and the same climate zones performing better. So also a really nice boost to multifamily. So when a recovery ventilator is required? Well, they're never mandatory, but they are prescriptive standard in roughly half the state for multifamily. Multifamily buildings under the current 2022 code have two choices for indoor air quality ventilation. And I've reproduced the climate zone map on the right for you to get calibrated on which climate zones. But you can do balanced ventilation in all dwelling units or any ventilation method and blower door testing of the units. They need to come in under 0.3 CFM per square foot of envelope. Now, when balanced ventilation is used in multifamily, recovery ventilators are prescriptive standard in climate zones 1, 2, and 11 through 16. Right? So if you use balanced ventilation in these climate zones, the standard design is going to have heat recovery. If you don't have heat recovery, you're going to take that 10% average compliance penalty, depending on what climate zone you're in, right? So if you guys are working on multifamily projects, you're finding balanced ventilation performs way worse than exhaust, that's why. And there's a minimum 67% recovery effectiveness and maximum 0.6 watts per CFM for balanced ventilation. Under the prescriptive method, of course, if you use the performance method, you plug in whatever you're installing. There's different standards for shared balanced ventilation systems in high-rise multifamily. What about the 25 code? We just had the 25 code approved, goes effect January 1st, 2026, right? For all permit applications starting then. So will it push recovery ventilators? I would say yes. Still not mandatory, but now multifamily buildings have a choice between balanced or supply. This is mandatory. They can't use exhaust. And they have to perform the blower door testing either way. Okay. And when in these climate zones, and notice they added 4 and subtracted 15 because it's 1, 2, 4, 11 through 14, and 16. Same thing, recovery is going to be prescriptive standard in more than half the state for these buildings. And the systems need to be equipped with a fault indication display, or FID, if complying prescriptively. Of course, if you comply via the performance method and your recovery ventilator doesn't come with an FID, you just check that box and you'll get dinged about 10% of your compliance credit, but you'll still get 90% of it. So I think this is really going to help adoption of recovery ventilators. Can't do exhaust anymore. So the comparison between the cost and complexity of balanced HRV to supply only is a more favorable comparison than HRV to exhaust. Yeah, we'll see. Now here's a little how-to on modeling these. If you are doing a performance method compliance model with exhaust-only ventilation, you just choose the default minimum and it calculates the CFM for you and puts in an exhaust fan. If, on the other hand, you want to do a recovery ventilator, you tell it to specify an individual IAQ fan. You create the HRV, in this case, a 55 CFM. Sorry, that label's wrong. 55 CFM HRV. It tells you the minimum is 53. Notice the minimum's a little lower with a balanced ventilation system for the same house than exhaust or supply. So there's a little help there. And then you tell it if your filters, recovery cores are accessible according to the ACM reference manual. That's a requirement. If you don't check that box, you're going to wipe out all of your compliance credit. And if it has an FID. When you add a recovery ventilator to a compliance model, the proposed design is the airflow, the watts per CFM, and recovery efficiency you entered. The standard design you're compared to for compliance is the same airflow you entered up to 125% of code minimum, at which point it stops increasing. So if your CFM is more than 25% above code minimum, you're going to get an increasing penalty because the standard design stays at 125% and you keep going up. Watts per CFM is default 0.7. And the outdoor air comes in with no heat recovery. So you're getting the whole benefit of that. And here you see that HRV that we specified, 55 CFM, 0.7 watts per CFM, balance, 67% sensible, 72% adjusted sensible. As I understand it, the adjusted sensible takes into account the fan heat, whereas the sensible does not. Best place to look up these metrics is in the HVI database. Here's a case study for you. I was working on these 6 new duplexes in Los Angeles, Climate Zone 8. Remember, Climate Zone 8 was one of those climate zones, fairly mild, didn't show huge energy savings from HRVs. The original compliance models I did for this client had a variable capacity heat pump and a condensing gas tankless water heater. The builder completely missed those features and called me in a panic. They used a ducted heat pump. They used a standard gas tankless. And here's the email I sent back to them. I have 2 options. We're tight on compliance before, so we have to compensate for the extra energy use. You can either add rigid foam to the walls, 1 inch of rigid foam, and above the roof deck, 1.5 inches, or add an HRV. If you add the HRV, you'll need to find space for the ducts to get the air around the house, or we may be able to make do with 2 through-the-wall units that don't need ducts. What do you think? And that's what we did. On the left is the compliance statement with what they actually installed. The dumb heat pump, the standard efficiency gas tankless. You see it was 1.2 EDR points away from compliance. On the right is what happened after we added the HRV. Boom, back in compliance. And the compliance impact would have been greater in climate zones 1 through 5 and 16, where the energy savings are even better. So let me cover now in the last section how to install these a little bit. The key questions that come up are, where do you put the recovery ventilator? Where do you run the ducts? How do you know how much CFM per room? Where do you put supplies and exhausts? And how do you get the ducts out of your envelope? Handle those penetrations. And finally, what controls, if any, do you give the occupants? This diagram on the right is the one that was done for my main house. I had a HERS rater, an HVAC consultant, a friend of mine, look at the CFM of the unit, the zones I wanted to cover. The office is that 51 CFM at the bottom of the screen, where I wanted to get 30 CFM in there for my daughter's COVID classroom. The 60 CFM up on top is the kitchen. There's a couple others to a living room and a bathroom and a bedroom. Notice the far right side of the house isn't covered by our HRV. There's a couple of bedrooms and bathrooms there, and I just couldn't figure out a way to get the air over there. So I thought, if I really see a problem, I'll put in a second one on that side. And he sized the ducts for me, and that's how I installed it. Again, in general, we're trying to get supplies into offices and bedrooms and living spaces, trying to get stale air out of bathrooms and kitchens. The ducts, in my case, are all up in the attic, but in new construction, they could be through the walls, they could be in a crawl space, especially when you use the small oval ducts that are designed to fit in framing. Or if you've got 2x6 framing, that's plenty of room for a 4-inch distribution system. Other configurations are possible too. So far, I showed you that diagram of a dedicated distribution system just for the recovery ventilator, right? That's the optimum, really the preference. But you can also do through the wall HRVs like shown here. The two on the left do the recovery in the box, and they do inlet and outlet right there through the wall. So there might be a little bit of mixing on a windy day, but generally they're proven to work. The one in the middle has a ceramic core. It's installed in pairs, and they reverse direction of the airflow. Pretty cool. So they temper the ceramic core by blowing out, and then they switch air direction, and now the incoming air runs through that tempered core, and then every minute or so they alternate. I thought that was pretty cool. The other option is ducting your recovery ventilator into your main HVAC distribution system. Here's why I don't recommend that. We're generally moving 50, 100, 150 CFM with our recovery ventilator, right? Any more than that, we're probably exceeding the amount we need for health, and we're using more energy than we need. But the duct systems for our HVAC systems, 3, 4, 5 tons, are designed for 1,500, 2,000 CFM. So if you put 100 CFM in a distribution system designed for 2,000, you really have no control over where that air is going. You get me? So that's why I really recommend a dedicated distribution system. And here's some pictures. On the left is a high-end install in a mechanical closet. They're using sheet metal ducts to get it out of that mechanical closet and into the OEM's distribution system. You can see each of those chassis allows to hook up to the sheet metal duct from the mechanical room, and then multiple 4-inch ducts are affixed to that chassis that takes the air around the house, both exhaust and supply. And I'll give a shameless plug here to a Santa Barbara area resident. He was a green building contractor. He's recently started selling these distribution systems for HRVs. So I don't mind plugging him because he's a 3C Ren guy, and he knows what he's doing because he's installed a lot of these. So I thought that was a pretty cool idea for his business. Now, if you combine a recovery ventilator and a ductless mini split, like I did in my ADU shown here, the SIPS panels going on, they allow for vaulted ceilings. We've typically built in California with vented attics to house in part the mechanical systems, right? We're also venting that attic to deal with moisture. So that's not the only function. But if you install a recovery ventilator in a bathroom with at least 20 CFM of exhaust, that meets the code requirement for local exhaust in a bathroom. 20 CFM continuous meets the requirement. So now you don't need a bathroom exhaust fan, and you don't need a soffit in the bathroom at all. So our bathroom has a vaulted ceiling. And the whole place has a vaulted ceiling, which is really nice for an ADU because it gives you the impression of more space. And of course, the ductless mini splits don't need an attic to run the ducts either. Even a ducted mini split can fit in a small soffit, and you can still vault the ceiling. Yeah, so the vaulted ceiling in this case has no means of reducing moisture, but the recovery ventilator in my mind is doing that job. It's continuously removing moisture, so there's no issue with it accumulating up there at the roof deck. Plus we've got balanced pressure, neutral pressure, as opposed to some pressure pushing it up there. Here's a snapshot of the HVI directory. They have this category of HRVs and ERVs, and you can search for all different brands and CFMs and find the recovery effectiveness here. So yes, Jay, ERVs do come with a condensate drain. In my experience, mine isn't creating any condensate. That may just be a function of my climate. So I just have the condensate drain going into a 2-gallon bucket and there's never anything in there. But in some climate zones, you are going to produce that and you're going to need to provide a drain for that. So what are your key takeaways? We're wrapping up here in our last 7 minutes. Key takeaways, questions? I sure hope we got to most of your questions. Yeah, Martin, I definitely advocate for him. Okay, Zach hadn't seen the quantification before, yeah. And that was a modeling study, don't get me wrong. I'm not able to directly measure the energy savings on mine. I probably could use the temperatures of the incoming and outgoing air streams to back into that, but I haven't done that. Yeah, got to understand costs. And the install is going to be a big part of the cost too. So you'll have to look at your contractors and which contractor installs it, right? I would say your HVAC contractor should install a recovery ventilator, but who installs the bathroom exhaust fans? The electrician. There's not a lot of know-how required there. So that means you're talking to a different contractor about ventilation than you're used to. In climate zone 3, Hank, so that's San Francisco down the coast. We saw really good energy savings actually, because there's quite a bit of heating energy use in climate zone 3 and not much cooling. So yeah, you should be in a happy spot for recovery ventilators. Okay, thanks, Zach. Glad that registered the sort of point beyond which added CFM may not be helping your health. Yeah. Forest fires. Yeah. I wish I kept the one I just pulled out. It was really nasty. My wife said, you got to get that out of my house right now. So in my experience, my filters are catching a lot of particulates, and we haven't had forest fires, knock on wood, affect our air quality much this year. But that is something MERV 13 filters capture. They capture diesel particulates, bacteria, viruses, and forest fire smoke and particulates are in that same category. So it's not hard to change a filter when you locate the unit like I did in the garage. It is hard when it's up above a closet that you have to remove shelves in to get to. So that's why the energy code requires that these units be accessible. Yeah, when we had forest fires a few years ago, I turned mine off. I decided, you know what, we're better off not having any air exchange right now. So it's kind of nice to have that ability. So I'll close with this slogan: RVs allow you to be your most productive selves. I'll give you my contact information here. I sure would love to hear your perspective as you spec these, install these, how they're working, hurdles you're coming up with, and happy to help with advice however I can. Yeah, we'll send a copy of this slide deck. All right. I'll leave it to you to sum up then.
Thanks, Nick. Yeah, thank you so much. Just a couple of things to go over before we close out today. Just a little pitch for our Energy Code Coach service that I mentioned earlier before. 3C Ren partners of Inbalance to provide free help both over the phone and online if you have any questions about Title 24. Go to the next slide, please. And with that, thank you so much. You can learn more at 3cren.org or contact us at info@3cren.org. And if you want to get our newsletter and learn more about courses that are upcoming, you can sign up at 3cren.org/newsletter. I think there's one more slide. And again, just want to let you know that we'll be sending you a survey to your email the next couple of days. We really welcome any feedback on our training series. And if you liked it and would like to receive more trainings like this in the future, the feedback is the best way to get that developed. And we also will be sending out the slides and recording, as Nick just mentioned. And just a little pitch of some upcoming courses that you may be interested in joining. We have a few next week. And then you can sign up for those at the link I mentioned before, and I will pop my email in the chat in case anyone has any questions about learning units for today's courses. And I believe that's it, unless anyone has any last minute questions.
Yeah, I just want to thank 3C Ren for allowing me to teach this class. This is a topic I haven't seen out there anywhere else. I feel really passionate about the improvement in health and human function that these can provide, while also giving energy code compliance. So I just want to thank you for allowing me to teach it.
Yeah. Really thank you for guiding us through this topic in such a great way. It's really informative, and I hope everyone got a lot out of it today.
Yeah. And 3C Ren territory is among those best favorable climate zones, right? We saw 1 through 5, and your territory includes a lot of 4 and 5.
All right, well, it is 11 o'clock, so I will go ahead and stop the recording and let you all go. But thank you so much again, Nick, for this course, and thank you so much for joining us today. Really appreciate it.
Enjoyed it. Thanks for all your participation, everyone being here.